talk about distributed systems in practice and in theory. And specifically, because the topic is just so large and we can just talk for days about this, we'll specifically focus on 3 architectural patterns that I've seen in my work at Google being used all over, and so the hope is that you'll walk away with some of the architectural patterns, knowing about them, and hopefully being able to apply them in your daily work. So before we get started, so I work at Google on Google's infrastructure projects. I worked on a variety of projects such as search infrastructure, working on search engine and distributed build system. Currently, I work on drive infrastructure. How many of you are familiar with Papers We Love community by any chance? Oh, wow, I see a lot of hands, awesome. So last time I checked, I'm not sure I found any chapters in Colombia, but there are. Great, awesome. That's awesome. So Papers We Love is one of my favorite communities. I've given talks at New York, Papers We Love chapter, and San Francisco, so it's awesome to hear that there's a big presence here. The community is, in case you don't know, is to come discuss computer science research papers and then figure out how we can apply those good ideas in our day-to-day work. And I founded an internal group at Google for us to be able to bring in the ideas and share the experiences, since a lot of the engineers have different backgrounds in computer science. And finally, that can be found online. So how did I get into reading computer science papers? I do not have a PhD. I did not go to grad school, and I was not forced to read a lot of papers, but I still love it very much. So during my senior year in undergrad, I took a class on AI, and besides the obvious of learning about the AI and all the related fields in biology and machine learning, the one thing that the class taught me is how to be able to read a research paper and then be able to summarize it, summarize the key takeaways, the key ideas, and then figure out if they are applicable to my day-to-day work. I would love to talk more about different strategies and techniques. So if you're interested, let me know, come up to me afterwards, and we can discuss good ways where you could spend a few hours and then say, okay, this paper is about these 3 main things, for instance. Okay, so let's take a brief stroll through computer science history and how different ideas apply to modern distributed systems. We'll start out in the 60s, where we started doing research on operating systems. And so here what we wanted to achieve is to be able to run more than one application on a machine. And so the paper came out, experimental time sharing system, the key point being time sharing. So it allowed us to figure out how to be able to run multiple processes on a machine and then split the time between them so that the operating system could suspend the processes, let a different process run, and then suspend that. And so to give us this perception that multiple different processes run on the machine at the same time. That's also when a paper by Dijkstra came out on cooperating sequential processes. So we started thinking about concurrency. What does it mean to run many different processes at the same time? And there are 2 key takeaways from this. One of them is that it introduced concurrency primitives, such as mutex and semaphore. So it basically allowed us to figure out how can we coordinate different concurrent processes, especially when they're accessing shared data. And another one is that we realized that processes can execute at different speeds. And so even if we have 2 identical processes, we can't actually rely on them to be able to finish at the same time. And so we needed to figure out different mechanisms, such as the mutex and semaphore, to be able to say, to be able to figure out how we can make sure that we coordinate them. So now we go into the 70s, so we started thinking more about the time, and we started thinking about the time in distributed systems. The paper on time clocks and the ordering of events in a distributed system came out by Leslie Lamport. And basically there, the main contribution is we started thinking about, okay, so now that we have the concept of time in our systems, how do we ensure that all the processes agree on the state of the world, and how do we specifically agree on the causality of events? So if 2 processes have been executing, how do we make sure that process A executed before process B if they need to coordinate some state, some shared state between them? That's also when the idea of pipelining was introduced. And that's in the 70s is when the hardware came out with the first implementation of hardware pipelining. What you see here is a 5-stage processor pipeline. And basically what it allows us to do is to increase throughput. And at every stage, we proceed with some part of the computation. And at the end, we get our result. But now, every single stage of the pipeline can be producing some work instead of being blocked on the previous stage. So now, in the 80s, we started getting access to the internet, thanks to the developments in ARPANET. And distributed consistency becomes important. So how we're having all these different participants in the system, all the different machines connecting to network, how do we agree on the same state of the world? How do we agree that all of the machines have the same knowledge of some fact? And so 2 important papers came out, View-Stub Replication by Barbara Liskov and Brian Ockey, and Part-Time Parliament about a decade later by Leslie Lamport. This paper is known for its distributed consensus algorithm known as Paxos. And then the View-Stub Replication paper introduced this algorithm. And as we realized that, as we started thinking more about the distributed systems, we realized that this is an important problem. And so about a decade after these papers were published, there was a second follow-up set of papers came out, Paxos Simplified and View-Stub Replication Revisited, because it was such an important problem. And we wanted to make sure that everybody understood how this kind of algorithm should be executed and how we agree on consistent state of the world when we have many different participants in the systems. So fast forward to 21st century. So this is the time when we started reconsidering large systems. This is finally when we have the business need to build bigger systems. And so we start turning back to the decades of research prior to this and actually figure out how do we build these systems correctly. And that's also when we started turning to a shared infrastructure. Instead of having every company, every team rebuild the same type of infrastructure that we need in order to build our systems, now other teams and other companies start producing it, start sharing it to be able to use it. So things like AWS and Google Cloud and Azure, now we're sharing this infrastructure. The projects that are worked on for build system, instead of having each team set aside a box on which they build and test their systems to be able to deploy them, instead we give them the shared infrastructure. We'll take care of all the machines, all the machine failures for them, and instead all they can do is just press build, and then the system will build for them, will notify them more issues, or maybe it will just deploy it right away. And so the main takeaway from this very brief stroll through research is computer science research is timeless. It can help us inform decisions. It's only now that we're starting to see the real business need to know about how to do distributed systems correctly. And so we want to make sure that it helps us inform our decision. We want to make sure that we're doing it correctly. And it also helps us mitigate technical risk. Reading a paper might take a couple hours, maybe a couple of days, maybe even a couple of weeks. But at the end of it, that just helps us understand a lot better what the trade-offs are. And instead of spending the months or whatever number of years it takes us to build a system and then only realize that we designed ourselves into a corner and then having to rebuild that again and not having a working system at the end, we could do the research first, understand what we're dealing with, and then move forward with it. So today we'll talk about the 3 architectural patterns, as I mentioned. One of them is staged event-driven architecture, and we'll specifically talk about how that applies to building robust pipelines. We'll talk about leases and how they were first introduced for distributed locking, and now how they can be used to also be able to tell liveness in a system. And finally, we'll talk about inaccurate computations. It's one of my favorite topics. The research only came out in the past decade, and the basic idea is we can sacrifice some accuracy and put a bound on how inaccurate we are and gain some performance and gain some robustness from the systems. So first, let's talk about staged event-driven architecture, and specifically how that applies to deep pipelines and to the search infrastructure pipelines that I worked on. So the paper came out in 2001. It was written by Matt Welch, David Culler, and Eric Brewer. And it describes actually a single machine web server architecture that allowed us to have robust pipelines. So as we discussed a little bit earlier, hardware pipelining was first introduced, and then we took this idea and then translated it to data pipelines. And so if any of you are working in graphics problem domain, this might be familiar to you, where we basically break up the computation into many different stages, pass the data through the stages, and then we get our final result. And so let's talk about this paper in a little bit more detail. So the paper defines a way to write web servers in a way that where web server can respond to increased load and decreased load and be responsive. So the paper describes a single stage of pipeline looking something like this. So this is the stage of the pipeline, and then we have an incoming queue of events, so some work being passed into the queue. And then we have one or more outgoing event queues going into the downstream stages. And so now locally, the stage itself has something like an event handler. It would actually process the messages, and then it'll have thread pools, or if you have distributed pipelines, maybe it's actually number of machines that you can spin up to support the load. And now the key here is actually the controller that we see here. So what the controller does is that it measures the incoming rate into the queue, and then it measures the outgoing rate. So if there are too many messages piling up on the incoming queue, what that means is maybe our stage is becoming a bottleneck in the system, and so we might want to spin up more extra resources to be able to catch up with the increased load onto the system. Now, if the incoming queue doesn't have that many messages coming in, but the outgoing queues have too many messages and the rate is increased, then maybe we're putting too much pressure now downstream stages. The work is not going to get done anytime sooner for the whole system, so we may want to choose to save our resources and turn down some of the machines or remove some of the threads from the thread pool, and instead slow down our existing stage. And so what this allows us to do here is every stage has some local knowledge about how it's doing compared to all the other stages in the pipeline. And it can make local decisions about whether it needs to catch up with the increased workload or whether it needs to slow down a bit and stop overloading the subsequent stages. So as I mentioned, this paper describes a single machine pipeline, but it generalizes very well to distributed pipelines. So let's take a look. Some of you might be familiar with how search pipelines work in general. I'll walk through it. If you're not familiar, this will be a very high-level overview just to understand why these queues matter. So we'll have a source client that uses RPCs. It could be anything, some process that allows us to find high-value URLs. Maybe we just want to discover as many URLs as possible. So it'll be sending us RPCs into the URL collector stage. And now we might have a database where we store some of the other URLs that we know about. And so now the URL collector will produce these URLs and also the rules. So the rules could be something like the football game is going on and it will end in 90 minutes. So keep updating the score every few seconds until the game is over. We don't really care about this football game because the score will always stay the same at the end of the game. And so we'll stop spending resources trying to keep it up to date. The other example would be a blog that gets updated once a week. So we want to make sure that we get the latest blog posts from this blog, but it only needs to be updated once a week. And so we'll feed this into the scheduler, which will run the business logic for us, and it will produce this set of URLs. And so now this scheduler will ask the crawler to go and actually fetch the HTML of the pages to get it updated. And then we'll feed these HTML of the pages into our indexes, update them, and then not shown here, the serving infrastructure will actually respond to query like cat pictures, and will actually retrieve us the set of relevant URLs. Okay, so now what we'll do here is, following the stage event-driven architecture, we'll put a queue before every single one of the stages. And so what it allows us to do is, we might have a very quick way to discover URLs. So we're going to put a queue right before the URL collector stage so that we don't lose any of the progress that we made so far in finding URLs. And if the URL collector stage is a little behind, then maybe we'll put it into the database and then we'll pick it up later. Now the scheduler has to run a lot more business logic. It's a lot more complicated than just taking the URLs and passing them on. And so it will need to resolve different sources of rules, for instance, where one source might tell us that update. For instance, the webmaster tells us this block is getting updated every day, and we actually know that it only gets updated once a week, and so we want to resolve this. And so the scheduler will now put a queue, and we'll try to figure out if it needs to spin up more resources, spin up more machines to be able to process and keep up with the load, or it can pare down. Now, going forward in the stages, we'll have a crawler, which is a very complex system, and so we might want to put it into the queue or into some persistent storage where we don't want to lose any of the progress we've made so far going down the pipeline, and we want the crawler to be resilient. We want the scheduler stage to be resilient to any kind of outages that might happen. And finally, the indexing, that takes usually even longer time to actually update all the indexes. And so we want to do something similar as well, where we have stages to help us buy time to buffer all the workload that we need to process. And then we'll build in other mechanisms to be able to respond to the increased and decreased load. Okay, so we discussed how we could do robust pipelines using staged event-driven architecture. Now let's talk about leases. How many of you are familiar with leases or use leases in your day-to-day work? Okay, I see a few hands. So the paper was written back in 1989, and it was introduced as a distributed locking mechanism. And we will also discuss how leases can be used as a heartbeat in distributed systems. So the paper was written by the two professors, Cheriton and Gray, and what it describes is this file server where a few processes might maintain a lock on the file, and then other processes coming in might want to read the files or do a write to it, at which point they need to ask for permission to do the write from every single leaseholder. And so what that means is that if the leaseholder is not responsive, then it will need to wait for the duration of the lease to actually proceed with the write and wait for the leaseholder to come back or for the lease duration to expire. So now what this allows us to do is we can ensure that the writes only by the approved entities can happen. And this allows us this way to do the distributed locking where the leaseholders can go away, the clients can go away, the client wants to do the writes, and then it decides it just doesn't care about it and goes away. And so we want to make sure that we can coordinate this. So while this paper introduces the mechanism of how distributed locking would work with leases, I think the more interesting contribution of this paper is actually the trade-offs that you can do in terms of the lease durations. So what are the advantages of short leases? Well, first of all, it allows us to ensure that there's no false right sharing. So if some leaseholder holds on to a file that it never actually cares to write to, then with short leases, at some point it would expire. An example scenario would be is the leaseholder decided to write to some file, and then after a while, it stopped writing to this file altogether. And so with short leases, it would expire, and then it would just go away. Another advantage of this is that we can ensure that the writes progress very quickly through the system. And so if the leaseholders are not responsive, then we don't have to wait that long for us to proceed with the write, because we will just wait very little time for the lease to expire and then proceed with our write. The advantage of using long-term leases is the following. So imagine that we have leaseholders that actually do lots of writes to the file. And so what it allows us to do is to ensure we take out a long lease on the file, and then we'll just proceed with our writes, and we don't have to renew it so often. So this minimizes the network chatter that we have to do to the lease server. So there is some server that actually keeps track or does all the bookkeeping of who's holding the lease, for how long, when will it expire, when did they renew it. And so by having long leases, we can ensure that we don't have to do this kind of communication overhead that much. So leases are used in a lot of modern applications for a few reasons. So there is the leader election, where we can ensure that leaders are selected for only a set period of time, and at the end of it, the lease will expire, and then this leader either has to ask for extension, or the leader can just disappear, and then a different leader could be elected. It can also be used for liveness detection. For instance, we'll actually look at the examples for this, but it would help us ensure that the clients talking to the servers, and the clients are alive and we keep track of it, and the servers are alive and we keep track of it. So imagine this build system that I worked on, and we'll call it the Patera build system. And so Patera creates a sculpture made out of clay, and he wants to cast it into bronze. And so he'll send his specification of what the sculpture should look like. And then the Patera build system, the one that actually does casting into bronze, say, okay, I accepted the work. So now they both know the work has started, initialized. Then Patera will tell us that he's still around, he's still waiting for the results, he's still interested in the results of the work. And then the build system will say, okay, my build is in progress, just keep waiting. And then again, the Patera will come back to us and say, okay, I'm still around, I'm still waiting for the sculpture. And then at some point, the build completes, and then we get our bronze sculpture back. So now, when does this fail? How do we use this to actually tell whether someone is not alive, whether some participant is gone and we cannot find it anymore? So I find it easiest to imagine it as a EKG diagram, like heart diagram. So we'll have uptick, where the client establishes a lease, and then we'll hear back from the server saying that the lease has been accepted. Now that's when the build starts. Now the client will renew its lease, and the server will say they accepted it, and then the build continues, because now they both agree that they're still around, they're still live in the system. Now we'll do this another way, another time, and we'll proceed. And now the client disappears. Something happened, the machine failed. The client will not be around anymore to actually get the results. So instead of wasting all these resources, the server will terminate the build. And instead of spending the resources, it will actually start with a different client's build. And this way, it would ensure that the build still would progress through the system. Similarly, if the server failed, it would never acknowledge that the lease has been renewed. The client now has the option of restarting on a different server instead of waiting around forever, possibly, for the server to come back alive. So now the important consideration here and the important trade-off is, how long should the lease term be? If you have a build that takes minutes to build because you have a giant project, a giant binary to build, then it might be on the order of minutes. And so you want to make sure that the lease term is not too short. Similarly, if you have a file server and the file, you only need to make the writes in milliseconds, then maybe a lease term should be a lot shorter. And also, it's important to make sure that you build in all the time interval tolerances here. So if the two data centers are very far apart, make sure to account for the longest possible round-trip network time to ensure that the lease can be renewed, and you don't fail to renew it just because the packet failed to get there in time. So now let's talk about inaccurate computations. As I mentioned, it's one of my favorite topics to think about. It's kind of a newer area of computer science research, but it's been used in systems without formalizing it before then as well. And specifically, we'll talk about how this concept is used in serving search results. So before, when we started building computers, we wanted our computers to help us do very tedious, very long computations that we didn't want to do by hand, and it would take us weeks or months, and then we would have to double check them. So we relied on the computers to be correct. Now, for many other problem domains, that's still the case. If you're a kernel developer, you still want your system to give you correct answers. In other problem domains, like encoding, decoding, with MP3s, your ears can't hear certain frequencies above and below certain thresholds, and so we just cut that off to make sure that the file is of manageable size. Similarly, if you're doing simulations, like Monte Carlo simulations, you already have a reduced version of what the world looks like. And so you can tolerate some inaccuracy because you're already only operating on the features of the world that you think are important. And so for some problem domains, some inaccuracy may be okay. So let's talk about how inaccuracy can be traded off for performance. BlinkDB is an interesting paper that came out, and it's also a database that talks about queries with bounded errors and bounded response time on very large data. This is useful when you're doing analytics and you want to see, for instance, is your company having actually better revenue based on the new features that you added, and you want to do this quickly before you do like the expensive investigation. And so this paper defines these queries that you can run. For instance, you're Netflix and you want to count number of Western movies that you have. And you want to do this within 5 seconds because you just want to see, do you want to optimize for the Western movies or do you want to optimize for thrillers or comedy first? Similarly, you could say, take as much time as you need, but give me a result that is as long as within 10% of the accuracy bound at 95% confidence level, that's good enough for me. I would do maybe a more thorough investigation later, a more thorough benchmark later, but for now I just want to make sure if I'm going in the right direction. And so this way you can trade off accuracy for performance, for the time you spend actually getting the answer, or for how far off you're going to be from the answer and how much you will tolerate. So as I promised, the example of using this in production is in search. Ignore the blue boxes here, and let's talk about just the red one. So the query comes in, you want to get the cat pictures. Okay, so now we can get it through the different index servers, and we have index shards and the index replicas to make sure that our system is resilient. And so now the request comes in, it gets it from the appropriate shard, from the appropriate replica, and serves the result. So now what happens if this replica fails? Well, it's possible that it has the most up-to-date data, so we could just wait around until it comes back up, and then our user will be very annoyed because they are waiting for a really long time for their answers. So maybe it's okay to serve them some stale data. If it's like a little summarization in the box, it's fine if it's not up to date. If they actually care, they'll just click in the link itself. And so this way we can keep the same response time to the user while also ensuring that we give them good enough results. Now what happens if the index shard fails? That might mean that it affected the results that you would return. And again, here we have a trade-off. We could wait around for a really long time for the shard to come back up and give the complete set of results. Or we could say, well, this is actually pretty lowly ranked. It's actually not that relevant to the user's query. And so maybe they will never ask. Maybe on the page number 7, they will actually would have seen this result. And in this way, we could just return to them results quickly and then have a robust way of responding to their queries while figuring out what might have happened on our end. And maybe the user will never actually care that this index shard was never available. So now if you start designing for inaccuracy, there's different ways to approach this. Again, just to reiterate, it's only applicable to some problem domains. But it allows us to simplify some implementation. So instead of taking care of all the edge cases, we could say, okay, we know what the category of failures is. And now we can focus on having the right metrics, having the right alerts to figure out if it even happens that often. And now we can do different types of testing, like fuzz testing, where we can ensure that our system is robust to users' not so good queries. Security researchers use this approach very often to ensure that the users can't break their systems. And now we can focus on generative testing. Instead of saying for this particular value, the result should be this, we could say for all integers, the result should be doubles because we're computing percentages. And now we can also do testing like photo injection tests.